So we discussed the Alice equation, and we assume that the power series solution is y equal to sigma an xn, which means that the initial value condition, which means that we are looking for power series solution about x equal to 0. But assuming that the solution is about x 0 equal to 0 is good for initial value condition imposing at x0 equal to 0. If the initial value condition are imposed at x0 equal to 1, for example, the initial value condition is y1 equal to a0, y prime 1 equal to a1. In this case, it is not reasonable to assume that the solution is sigma an xn. Instead, we should assume that the solution can be expressed by power series about x0 equal to 1. That is, we should assume that the y2 of this form, not an xn, but an x minus 1n. Okay? So, for our Alice equation, for example, for this equation, how to find the solution of this form? Of course, we process as before, computing the second order derivative of the power series expression for y. The second order derivative can be computed by differentiating this power series expression turn by turn, and you see that the y double prime is this n minus 1 an x minus 1 n minus 2. Okay, then we're switching the summation index. That is, we let n minus 2 to be a new n. That is, the old n is the new n plus 2, and the new n is range from 0 to infinity, because the old one is 2 to infinity. Okay, so switching the index, we see that the y double prime can be written in this way. So the equation, substituting this y double prime and y into the equation, we see that 0 is the y double prime minus xy. That is, this is y double prime minus xy, here. This is y. Okay. But now we have sorry, I missed something. Here, this is not xn. This should be x minus 1n. This is a misprint. Sorry. This x here, and that is here, should be x minus 1. This is a misprint. So, so these two series is not easy to combine together, because this x is x minus 1, and this is also x minus 1. But here we have an x here. The method is to write the x here by 1 plus x, then minus 1. So we have an x minus 1. Okay. Then these two functions, the constant function 1 and the linear function x minus 1, multiplying the second power series separately, and we have no place here, so I copy this last line to the next page. Next page is here. So also this x should be x minus 1, the misprint. Okay, so so after splitting these two into two terms, we have the one multiplied summation is an x minus 1n, and then the x minus 1 multiplying this summation, we can move the x minus 1 inside the summation, and then this increase the power of this x minus 1. Previously it is n. Now after move the x minus 1 inside, this becomes n plus 1. Therefore this becomes n plus 2, n minus 1, n plus 1, n plus 2, n plus 1, an plus 2 minus an. That is we combine these two summation. We combine these two power series. But as I emphasized several times, the xn in the first summation is x minus 1, not x. Okay. So combine these two terms, we obtain the sigma n from 0 to infinity n plus 2, n plus 1, an plus 2 minus an. Then this is x minus 1 to the power n. Okay, and then we copy the third power series here. And copying this down here and switch the summation index. The previous n is from 0 to infinity. We replace the n plus 1 by a new n. Then the new n is from 1 to infinity. And this is an minus 1, x minus 1, n. Okay. Then we can combine all together. But the first term in the first summation, the x minus 1, the power of x minus 1 is from 0 up. But for the second, it is from 1 up. Okay. So we need to write the term corresponding to n equal to 0 for the first summation separately. That is, when n equal to 0, this is 2 multiplying 1, then a2 minus a0. Okay, this is the 2a2 subtract a0 corresponding to the term for n equal to 0 in the first series. And then the first series, after taking the term corresponding to n equal to 0 aside, we have the sum from n from 1 to infinity. And then 1 from infinity can be combined with the second summation. That is, n from 1 to infinity, n plus 2, n plus 1, an plus 2 minus an. This is the coefficients of x minus 1, n from the first summation. Then subtract an minus 1. That is, this an minus 1 is the coefficient of x minus 1 power n in the second series. So we obtain this, and as before, this is x minus 1, not x here. Misprint. Okay, sorry. So from this result, and the left hand side, what's the left hand side? The left hand side is 0. Left hand side is 0. Therefore, we conclude that we conclude that 2a2 minus a0 is 0. Therefore, a0 is 2a2, and also this should be 0. This should be 0. The coefficient of the x minus 1 to the power n for the power series in the last line should be 0. That is, when n is greater than or equal to 1, this should be 0. That is, this should equals an plus an minus 1. So we obtained a recurrence relation between the coefficients an, but this relation involves 3 terms: an minus 1, an, and an plus 2. So this makes it difficult to compute the coefficient an. What should we do? We copy this relation. Copy this relation we obtained to the next page. Okay, that is here. What can we do? We can compute the coefficient using a0 and a1. So a2, assume that a0 and a1 are given. Then from this a0 is 2a2. We obtain a2 equals half of a0. So a2 is half of a0, and so we have a0, a1, and a2 is half of a0, and then a3 using this recurrence relation, take n equal to 1. We obtain a3 is here n equal to 1. 1 plus 2 is 3. 1 plus 1 is 2. So 2 multiplying 3 is 6. Therefore, a3 is a1 plus a0. When n equal to 1, the right hand side here is a1 plus a0. So a3 is a1 plus a0 divided by 6. Okay, and this is a1 over 6 plus a0 over 6. And then a4. For a4, we take n equal to 2. we take n equal to 2 in this relation, then A4 is A2 plus A1 divided by when n equal to 2, the coefficient on the left hand side is 4 multiplied 3, that is 12. So A4 is A2 plus A1 over 12. But we want to express everything in A0 and A1. So we need to substitute the A2 here using the expression for A2, that is half of A0. Therefore, this is A0 over 24 plus A1 over 12. And then we can compute A5 in a similar manner, that is A0 over 30 plus A1 over 120. And then in this way, we can, although we can, maybe we cannot obtain a very beautiful, elegant formula for an, but we can determine as many terms of an as we wish using A0 and A1. So then we can obtain the expression of our y, the solution. That is A0, 1 plus half of x minus 1 square. Why this is x minus 1 square? So this is the square term. Square term, that is A2. A2 is half of A0. So A2 is half of A0. Correspondingly, the coefficient of x minus 1 square is half of A0. But we subtract A0. We move A0 inside, in front of everything. Therefore, this is half of 1 over 2. The coefficient is 1 over 2 here. So then A3. Then we write the term third order term, x minus 1, 3. And that is A3. A3 have two parts. A3 has A0 part and A1 part. So we write A0 part here. A0 part, the coefficient is 1 over 6. So this is x minus 1 over 3 over 6. Okay. And then the fourth order term. Fourth order term, similarly, that is A4. The coefficient is A4. But A4, we have two parts. The part involving A0 is 1 over 24. Therefore, this is y24 here. And of course, we can also have the fifth order term, x minus 1 power 5. Okay. So that is A5. A5, the A0 part of A5, the coefficient is 1 over 30. Therefore, this is y30 here. So we are content to write 5 terms. Of course, if you want, you can write more terms to get a more better result. Okay, but that will be more complicated. And we stop here. We just write 5 terms. But to make this equality, you need to add the dots here to indicate there are many terms we have not write down explicitly. Okay, so this is the part of the solution involving A0. And also the terms involving A1. So A1 is the coefficient of x minus 1. Okay, therefore this is A1. So the coefficient is 1 here because we move A1 outside. Then the second order term, x minus 1 square. X minus 1 square, that is A2. A2, the value of A2 does not contain the A1 part. So for this A1 part, we do not have the square term. So we have the first order term and then third order term. Second order term will not appear in the A1 part. Okay. Then so the third order term, that is A3. A3, the A1 part, the coefficient of A1 part of A3 is 1 over 6. This is y6 here. Then the fourth order term is the A1 part of the A4, of the coefficient A4. But the A4 is here, the A1 part is 1 over 12. So this is y12 here. Okay? And similarly, the A1 part of A5, the coefficient of x minus 1 to the power 5 is 1 over 120. Therefore, we have 120 here. So, and as before, we write the dots to indicate we have more terms which have not been written down here explicitly. So this gives us a power series solution of our Alice equation about the x0 equals 1. This is natural to if you impose initial condition at x0 equal to 1. But we see that we could not explicitly express the coefficient an from the recurrence relation because the recurrence relation involving more than 2 terms, so it is difficult, if not impossible, it is difficult to write a very elegant expression for an. Therefore, we have to write the part of the solution. Okay, here we write only 5 terms. If you want, you can contend x minus 1 to the power 6 more terms. Okay, so because we do not have the expression for an, we cannot study the convergence of these two solutions. This is y1 and this is y2. We cannot study the convergence of these two series and find the radius of convergence. Okay, we could not do this without the expression of the coefficients an. But using the result we will describe later, we can see that the radius of convergence of both y1, this is y1, and this is y2. The radius of convergence for both y1 and y2 are all infinity. That is the series expression for y1 and y2 converge at every x, every real number x. Okay.